For our next topic, we're going to look at limits at infinity. And this infinity here basically refers to the question, what happens to f of x when x becomes very large? And this could be very large positive or negative. So let's look at an example of what we mean by that. So here we take f of x equal to x squared minus 1 divided by x squared plus 1. And so we want to know what happens if x becomes very large. And we'll also denote that as x goes to plus infinity. So we can plug in some numbers. So for instance, if you set x equal to 1000, then f of 1000 becomes 1 million minus 1 divided by 1 million plus 1. And if you calculate that with your calculator, that's approximately 1. And you can put in 10,000, 100,000. What you'll see is that the value that you get out for f of x gets closer and closer to 1. So in this case, we say that the limit for x going to plus infinity of x squared minus 1 x squared plus 1 is equal to 1. And you can do the same thing if you take x going to minus infinity, so you let x get larger and larger but negative, x squared minus 1 x squared plus 1. So for instance, if you put in x is equal to minus 1000, x is equal to minus 100,000, and so on, you'll get pretty much the same thing. So f of minus 1000 is again going to be very close to 1. Same thing here. And we can conclude again that the limit is 1. We'll see a couple of rules in the limit law section that allow us to calculate these a bit more formally. If you're wondering about the graph of this function, what we know is that this function becomes 1, or it gets closer and closer to 1 when x gets bigger and bigger on the positive or the negative side. You can also calculate if you plug in 0 for x, the function value is negative 1, and the graph of the function is going to look like this. And in particular, what you see is that as x gets bigger and bigger, the function gets closer and closer to the line y is equal to 1, but it never reaches that. So this is going to be an example of a horizontal asymptote. Before we get to horizontal asymptotes, let's quickly look at another example. If we take e to the power minus x, and we let x go to plus infinity, what do we get? Well, for that we can look at the graph of the function. We know that this function has the following aspect. So it's very large, and then for x is 0, it becomes 1. and then it goes to 0 as x gets larger and larger. So here, from the fact that the function becomes less and less when x becomes bigger and bigger, we can decide that the limit of e to the minus x is equal to 0. So we can define what it means to take the limit a little bit more formally. So here we say that if f of x is defined on an interval a all the way to plus infinity, and if we can ensure that f of x gets as close as we want to a value L by taking x to be large enough, then we say that f of x approaches the limit L as x approaches plus infinity, and here we use the notation lim x going to plus infinity of f of x is L. The same thing, same definition holds if you go to minus infinity, but now you have to change all the signs. So here we want f to be defined on an interval starting at minus infinity, roughly speaking, and going to a value a. And f of x has to get as close as we want to a value L by taking x large enough but negative, and then we say that f of x approaches the limit L as x approaches minus infinity, and here in the notation we say x goes to minus infinity. So with that in mind, already briefly touched upon horizontal asymptotes. So horizontal asymptotes, vertical asymptotes were the lines that sort of attracted the function in the vertical direction. Horizontal asymptotes are the lines that the function tends to in the horizontal direction. So let's recap an example that we had earlier on. So x squared minus 1 divided by x squared plus 1. Here we said the graph looks like this. We have a horizontal line like so, and then the function does this, and then it goes like that. So here the line y is equal to 1 is going to be a horizontal asymptote, because you can see it's a horizontal line that the function tends towards. So more formally, we say that a horizontal asymptote is a line y equal to some value L, so it's a horizontal asymptote if, and then a very similar condition as for vertical asymptotes, lim of f of x for x going to plus infinity is L, or the limit of f of x going to minus infinity is L. So, and it's again one of the conditions that has to be satisfied here. So if one of the following holds. If both conditions hold, that is great, it's still a horizontal asymptote. So let's do another example. So here let's take y is equal to e to the power x and find the horizontal asymptotes. So we know e to the power x has the following graph. It tends to 0 when x is negative, and then it blows up when x becomes positive. So, and in particular, here we have that the limit for x going to minus infinity of e to the power x is 0. So from that we have that the x-axis, y equal to 0, is a horizontal asymptote. And as another example, maybe a bit more tricky to calculate this, so let's look directly at the graph. So here let's take the function y is equal to e to the power x minus e to the minus x divided by e to the x plus e to the minus x. So this function is called the hyperbolic tangent. And is a very important function in machine learning. I'll just give you the graph, tell you what it looks like. So this function has two horizontal asymptotes, one for x is equal to plus 1, y is equal to plus 1, one for y is equal to minus 1, and the function itself looks a bit like this. And then it tends to the function. You can try to calculate that. So if you look at x going to plus infinity of e to the x minus e to the minus x, and then this here. Think a little bit about these individual factors. So as x becomes larger and larger, e to the power x is going to go to plus infinity. E to the minus x is going to go to 0. And then here, e to the x again is going to go to plus infinity. And this e to the minus x is going to go to 0. So what we're left with is this will become bigger and bigger, this smaller and smaller. So this limit becomes limit for x going to infinity, e to the x divided by e to the x, and that's equal to 1. And then you can do the same thing for x going to minus infinity, e to the minus x minus, sorry, plus x here, minus x minus x. And now it's going to be this term that's going to go to 0. This term, if x becomes more and more negative, e to the minus x is going to become larger and larger in the positive sense. This goes to 0 and this goes to infinity. And you see in the limit, it's these two terms that matter, and so we get that this becomes equal to minus e to the minus x, e to the minus x, and that's minus 1. Again, with limit laws, this will become a bit more clear to calculate. Before we move on, just want to make a quick note. So a function can have 0 horizontal asymptotes, it can have 1 horizontal asymptote. We saw that here. So here we have 1 horizontal asymptote, and it can have 2 horizontal asymptotes, like this function right here. But that's the maximum. You cannot have 3 horizontal asymptotes, because what happens is the horizontal asymptote is what happens at plus or minus infinity. And if you contrast that, you can have an arbitrary number of vertical asymptotes. Arbitrary number of vertical asymptotes. In particular, you can have an infinite number of vertical asymptotes, and we saw that, for instance, when we looked at the tan function. Then the function looked like this, and all of these lines are vertical